Aloha everyone, my name is Tayler Pave, and during the spring semester of 2017 I have been working on the EKY project with the supervision of Dr. David Garmeyer. My group members are Richard Choi, Alexandra Myers, Ian Umetsu, Tian Tran, and our team lead, Tayler VT. Throughout this video, I will be sharing background info on what the EKY project is and where the motivation for this project came from, our goals, and how I contributed to this project. So let's begin with the first topic. What is EKY all about? The motivation for this project first started with the hundreds of water wells that are located around Hawaii and other tropic U.S. territories like America Samoa. Those water wells lead right to our freshwater aquifers that provides the fresh water to the local population. To make sure the aquifers provide healthy drinking water, field scientists often have to go out to these hundreds of wells to perform tests to verify the water is in good condition. Not only is this task taxing, but it can be dangerous for the field scientist. The water wells are located far from civilization, and not only that, the equipment the scientists have to chug along with them is probably not the easiest task, nor is it good for the equipment. This is where the idea of the EKY project started. The idea was to simplify the data testing by instead having a standalone water measurement system without limited or no human presence required. Like the project name, we are seeing or being aware of the fresh water, EKY. This is not a small-scale project. This type of project affects many people, from the engineers who create the sensors, geologists who survey the land, chemists who test the waters, biologists, and more. The engineering goal for this project was to create a standalone system that will monitor the characteristics from a remote location. To fulfill this, there are various subsystems. One was to focus on the functionality of the creation of the sensors, one was to calculate the power system, and last was to program the microcontroller that was going to be the brain of the system. The subsystem I focused on was the off-grid power system. To achieve this, the first steps were to analyze the power that was needed, then figure out what components were needed for the system, and then test and integrate the system with the other subsystems. There were a few challenges with an off-grid system. The main obstacle is that we would not have any wall outlets, meaning there was no source of consistent power available. However, the solution to that is renewable energy, utilizing the power that comes from nature such as wind or sun. After doing some research, we found that solar panels were a more reasonable source to practice with than the energy from a turbine, considering the circumstances of this project. After researching the main components needed for a standalone system, we were able to find that we needed a charge controller, a battery, and of course a solar panel. There are so many varieties that we did not know what to get, so we calculated for some values for an ideal power system, as you'll see in the next few slides. First, we had to figure out how much power is required by the system. Not only that, but we had to prepare for the worst case scenario, such as if there was no sun for 3 days. Calculating the step motor, Raspberry Pi 3, and the sensors, we calculated that the system uses 49.92 watt-hours for 1 day. But preparing for the worst case scenario, such as if there were no sun for 3 days, the system would use up at least 149.76 watt-hours. When considering which battery to choose for the system, we thought about how batteries are usually 80% efficient, and how ideally you do not want a battery to discharge over 50%. So calculating this, the most ideal battery would be a 12-volt motorcycle battery with 18 amp hours, which would provide 216 watts, which is well over the power required for the whole system. The way we had chosen the solar panels was that we would need to be able to choose the correct size solar panels that'll allow us to charge the battery within a reasonable amount of time. To do this, we first calculated the sun hours of the air we would receive daily. We found that 15-watt solar panels would be a good choice and would generate at least 60 watts a day given the average 4 sun hours to our area. This shows that our battery will be fully charged in 2 to 3 days. Although we have completed the calculations to find the ideal components needed for the standalone system, we have yet to put it to the test. Some of our future work includes further testing and integration with the other subsystems to make sure we have a fully functional system before the system is brought to America Samoa for further testing. There is still a lot more to work on. However, the topic of renewable energy is an exciting topic to further research. Mahalo for watching.